Okay, so basically in our discussion previously, we were looking at some famous or popular deep CNN architectures, right? And what we have already seen, basically we started our discussion with LeNet, which was 1998, right? And then AlexNet 2012, and then VGG, okay? So these were few of the, you can say, popular architectures that we had seen, right? VGG has two publicly available versions, VGG 16 and VGG 19, and both of these are available. And these are very homogeneous architectures, right? As I told you, 3x3 convolution and always pooling with window of 2x2. So it's like a very homogeneous architecture, right? So if you are solving a problem that is not very complex, okay, a limited number of classes and sufficient training data, so it's a good starting point that you start either with AlexNet or VGG, right? Do not directly jump to more advanced architectures like Inception or ResNet, as we'll see today, okay? Maybe if your problem is complex, then it's okay, right? But it's not a good idea that you directly start with a very complex architecture for fine tuning or feature extraction. It's always a good idea that you start with some baseline like AlexNet or VGG. And if you are not getting something which is acceptable, maybe then you can actually move to more complex architecture, right? Sorry, this is ResNet, okay? Just a typo. Okay, so today we'll be starting our discussion with the Inception family, right? Within that, we'll cover V1 in detail, then V2 and V3 we have already know to some extent, right? And then we'll see exception in detail. And later we'll move towards ResNet and DenseNet, right? So let's start our discussion with the Inception family, right? The Inception network is considered a very important milestone from the perspective of advancements in convolutional neural networks, right? And why is it so? Because before Inception, there was a trend. And what was that trend? That people were making deeper and deeper network simply by stacking layers and making the network deeper and deeper, right? So if, for example, I have sufficient hardware resources, so maybe I have a network like this, and I say, okay, I have more hardware, so I will keep on adding layers, right? And I'll try to make it as deep as possible, as much as supported by my hardware, right? So on the other hand, when the idea of Inception is that not only we increase the depth, but there's a new concept which is called wider, right? That not only we are increasing the depth of the network, we are also making the network wide. Now, what does that mean wide? It will become clear when I show you the subsequent slides, right? So it's just you can say the introduction, right? So the first key point is that in addition to depth, we focus on the width as well. What is width? We'll see in a while. Another focus was that they actually strive to reduce the computational complexity of the model, right? Because once you increase the depth or the width, as we'll see, so naturally we'll be increasing the computational complexity, right? So a key focus of the Inception family was that how can we scale up the neural networks without too much increasing the computational complexity, right? Means the total number of parameters should remain manageable, right? And if the parameters are lesser, right? So it means that actually the number of multiplications you will be having in the CNN, they will also be limited. Okay, so as I told you that the popular versions of Inception are V1. Another name for Inception V1 is actually GoogleNet, okay? And if you see GoogleNet, you see it is spelled like this, that this part actually is just to pay tribute to LeNet, which was the, you can say, one of the very earlier CNNs, right? So Inception V1, another name is GoogleNet, then you have V2, V3, so, and then you have V4 and Inception ResNet. This was actually a single paper which introduced these. So each version is an iterative improvement over the previous one, right? And what is common to these? Common to all of these is something which is called the Inception module, right? That rather than simply having convolutional layer, now we'll introduce something which is called Inception module, as I'll show you shortly, and will be, you can say, repeating that module and making the network. So this is basically the paper for the first version of Inception, which is Inception V1 or Google Net, right? You can call it whatever you like. So just to give you an idea that you see when we had this course for the first time, right? So maybe about a couple of years back. So you see, still it was quite popular that you had around 11,000 citations for this paper, which is describing Inception V1, right? But right now, maybe a week ago, you see this number has almost multiplied by 3, right? So it means that it is an exponential growth that more and more people are actually using deep nets, and they are referring to this Inception V1, which was a major milestone in the development of CNN, right? This is, you can say, a screenshot of the paper. It's an easy to follow paper, right? So you can actually go through it to see more details, right? So the reason is that, as I told you in the introductory discussion on this topic, that there are many architectures, right? And it is not possible that we see each and every possible detail of each and every architecture, because the course is not on CNN, the course is on deep learning. So we can only dedicate some limited time to this topic, right? So that's why whenever we are studying an architecture, we'll be focusing only on the key aspects, right? There are many low-level details, which if you are working specifically on some particular architecture, you can always see the research paper associated with that architecture, or there are many tutorials or blogs in which the papers are explained in a very easy to understand language. So if the paper is not easy for you to understand, there is a review of different papers on different blogs. You can actually read them, and you can have the low level details, right? So another, before the technical concept, another important aspect is that this name Inception, right? That maybe many of you already know, right? But just for completeness, I will tell again that why did the authors come up with this name, right? So basically, there's a very well-known internet meme from this movie Inception, right? Which says we need to go deeper, okay? And from this, inspired from this, you can say internet meme, the authors actually came up with the name Inception, right? And they have actually mentioned it in their paper. So this is a small, you can say, extract from the original paper, right? Where we say that in this paper, we'll focus on this, and code named Inception, right? So this is a code name they have given to this model, which derives its name from the famous "we need to go deeper" internet meme, right? So you see, it's a bit rare that a research paper is actually citing an internet meme. You will not see it frequently in research papers, right? But that's the way it is. So this was basically their source of inspiration. So they called it Inception, right? And of course, at the time this model was proposed, they only called it Inception, right? Because at that point, there was no version 2, version 3. Okay, when you propose something for the first time, it is just that thing. So at that point in time, it was called Inception, not V1. Later, when some iterative improvements were suggested, so it was at a later stage that just to, so that people can easily discriminate between different versions, they use this terminology V1, V2, V3, right? So at that point in time in 2014 or 15, it was just called Inception, nothing else. Okay. Now let's come to some technical discussion that what is the key motivation of this Inception module, right? So you see, we know that in a CNN, the key operation is convolution. We perform convolution with the filter, right? And we expect that the filter will detect some features from the image or input volume, whatever we are feeding it. Now, an important aspect that we did not discuss is that suppose we are trying to detect an object, maybe a dog in an image, right? So depending upon the distance of the object from the camera, the size of the object will vary, right? So you see 3 different images, all have the same object, but the position of the camera with respect to the dog is different, right? So suppose I carry out filtering with a 5x5 filter, right? So suppose I place a 5x5 filter maybe here, and maybe a 5x5 filter here. Okay, the filter size in both the cases is same, but since the size of the object is different, so maybe in this case, the 5x5 filter is like partially or containing almost all the face of this object. Whereas in this case, this 5 by 5 filter is just containing a uniform patch, right? If I show you only this patch, there is actually no feature in it. There is one single color, right? Maybe here you will have some useful feature, here you will have eyes, right? But there are many regions in which you will have no significant feature. So now you see that there is a problem of a scale, right? That since the size of the object can vary, so if you apply a very large filter size, right? For example, 5 by 5 or even 7 by 7 is a large filter size for this. So you are actually capturing more of a global information, right? Because you are having the information of the complete face of this object. On the other hand, if the object is large and I'm applying 5 by 5 filters here, so you see at one point in time, the filter is containing a small part of the face, right? Maybe eyes or nose or maybe ear or something like that. So it is capturing the local information. So what we infer is that if you have a large kernel size, and large means relative to the object, right? So you are capturing the information which is more of global information, right? The complete face, the complete body, and so on. And on the other hand, if your filter or kernel is small with respect to object, then mostly you are capturing some local information, right? Different features of the face, for example. So now the question is that since there is a huge variation of size, so how do we choose the right kernel size? Kernel is actually just another name for filter, right? So don't actually think what is kernel. Kernel is just another name for the filter, okay? So since we don't know that in our data set, what is the distance of the object from the camera and what would be the size of the object that we are trying to recognize. So there's always a challenge that how do we choose the right size of the filter, right? So the idea of Inception is that instead of you decide that, okay, I will choose a 5 by filter or 3 by 3 filter, or I'll do pooling. So we say, okay, let's at a given layer, we do multiple things, right? And we let the model choose itself that what is the best operation for this particular layer. Now, what does that mean? That instead of having one single filter, okay, they say, okay, at the same level, it means at the same input volume, you will apply multiple filters. Multiple filter means on the same volume, we can have a filter of 5 by 5. You can also have 3 by 3. And you can also do maybe pooling rather than doing convolution, okay? And maybe a filter of 1 by 5, 1 or 7 by 7, whatever you choose, right? So you will have filters of multiple sizes applied on the same level, means same input volume. So actually what will happen now? That your network is going wider rather than deeper. Okay, so this is the terminology that we discussed in the beginning of the lecture, that the idea of Inception is to make the network wider. And this is what do we mean by wide. It means applying multiple filters of different sizes to the same input volume. Actually, your volume is undergoing multiple different transformations, right? And what do you do? Once you have all of these outputs, you concatenate them, you stack them together, okay? And then you can let the model choose which of these is actually useful. So all of the discussion that was presented in the subsequent couple of slides, it can be summarized by this visual illustration, right? Which will actually sum up and will help you better understand how things are working, okay? So you see, this is some input volume, whatever is the width, height, and depth. And what we do is on the same volume, we are doing a convolution with a 1 by 1 filter, with a 3 by 3 filter, 5 by 5 filter, and we are also doing pooling. So each of these operations is producing an output, right? So maybe a 1 by 1 convolution is producing this particular part. Similarly, 3 by 3 is producing this, and so on. So you see, we have these different outputs, and we concatenate them together. So we now have, you can say, depth, which is actually the sum of depths of all of these operations, right? And what is the depth of each? It depends upon the number of filters, right? For example, if I'm using 10 filters of 3 by 3, then this depth would be 10. If I'm using 50 filters of 1 by 1, then this number would be 50, and so on, right? It's actually the same idea. The only new concept is that we are concatenating the outputs of different filters. And not only convolution, we are also doing a pooling, and we are also concatenating it, right? So it means You are doing almost everything on a single layer, and then you stack the outputs together to have a volume which has relatively larger depth, right? Okay, so as you must have already guessed that once we are doing convolution with multiple filter sizes, so definitely we are compromising on the computational cost, right? Because previously on one layer, we were doing convolution with one particular filter. Now multiple filters of different sizes are being applied to the same volume, right? And the problem is that you see, suppose I have a volume, okay? And suppose the depth of this volume is M, okay? Now, if I introduce one more filter, so you see, we say that the depth of the filter is always equal to the depth of the input volume. So it means if the depth is M and you introduce one filter, so the depth of this filter is also M, right? It means you have to do M convolutions because there are M channels. And instead of one, if you introduce two filters, it means you have to do additional convolution 2 into M times, right? Because once you do convolution, you have to do it on the complete depth. And similarly, if there are N filters, so it means you are increasing the number of convolution by N into M times, right? So basically, for a linear increase in the number of filters, there's a quadratic increase in computation, because if you increase one filter, you don't have to apply, you have to apply it in all the M channels, right? So that's why the increase in the computation is much more. So in order to solve this computational complexity, and what we want is that we want multiple filters, which is good, but we don't want too much of computational complexity, right? So we want a solution in between. So there's a new concept which was introduced in this Inception module, which is called a one-by-one convolution, right? An extra one-by-one convolution. And what is the objective of this one-by-one convolution? One-by-one convolution, I'll explain in detail in the subsequent slide. It is actually a mechanism or a special type of convolution which allows you to control depth of any input volume, right? Just like for spatial pooling, we use, for controlling the spatial dimension, we use pooling. If we want to control the depth, we can use one-by-one convolution. Now, let me tell you maybe how this will work. So let me just explain it maybe on the board so that you understand well that how things are working. Okay. So we assume that suppose we have an input volume which is like, this is our input volume, right? And we say it is say 64 cross say 100. Depth is 100, okay? And I apply convolution with a filter of 1 by 1. When I say 1 by 1, actually filter is 1 by 1 by 100, okay? Because the depth, this number and this number should be same. This we already know. And we apply 1 by 1 convolution, and suppose we apply 20 such filters. So what would be the output volume? The output volume would be 64 cross 20. So now you see, here we had a depth of 100. And here we have a depth of 20. So we have reduced this depth. Spatial dimensions remain the same, because when you do convolution, spatial dimensions do not change, right? Provided we are doing padding. But since it's a 1 by 1 filter, so even padding is not required, right? Because it's a 1 by 1 filter. So spatial dimensions remain the same. But by choosing this number 20 to be anything, you can actually control that what would be the depth of my output volume, okay? So now let's go back to the slides so that we continue from there. Yeah. Okay. So you see, we have any volume, we apply 1 by 1 convolution, and it actually helps you to reduce the depth. Now let's see some more details that how this can be useful. Okay. If you see a 2D matrix, a 6 by 6 matrix, if I ask you to do 1 by 1 convolution, so you see it is just multiplication by a scalar. That you see, if my 1 by 1 filter is say this value 2, so you multiply everything by 2 and you get something like 2, 4, 6, 10, and so on, right? So this does not seem to be a very useful idea, right? Because if we see it in 2D. But if you see it from the perspective of multiple channels from a volume, then this idea of 1 by 1 convolution is actually very interesting, right? Why? Because now you see the filter is 1 by 1, but its depth is 32. It means there are 32 values, 4, 6, 2, -1, 3. So there are 32 values like this. And when you do convolution, you have 32 values here in the depth. So it means these 32 values in the filter, they are multiplied by 32 values which are here along the depth, and you get one number which goes here. Then you move the filter one position to the right, you multiply all 32 values together, you get the second value which comes here. So you keep on moving the filter on the image, okay, and eventually you have a 6 cross 6 output, right? So if you apply one filter, you have a 6 by 6 cross output. Now, it is important to understand that what is actually happening here. When you have 32 values in the input and 32 values in the filter, okay? So when you are doing the dot product, what is actually happening is that, let me just explain here. Maybe let's assume you have three values, okay? Say x1, x2, x3. So these are actually 32, but I'm explaining with only three values. And in the filter, you also have three parameters, W1, W2, W3, and actually they are 32 in this example. So what you are doing, you are actually multiplying the corresponding values together, okay, and adding them all together. So now you see, if for example, I don't want this value x1, my network thinks that this x1 is actually a useless value. So I can make, the network will learn its weight, which is close to zero, so that its impact is actually nullified, right? This is like selecting which is useful and which is not useful. Similarly, if this x3 is very important, then maybe my network will learn a weight which is high, so that when I add these together, x3 will have a high value of weight. It will have high contribution in adding all of these, right? If I don't want x2, network can say, okay, this W2 is zero, so there is no contribution of x2. So this is like selecting, this like a weighted combination of your 32 values, and something, if it is useful, it will get a high weight. If it is not useful, it will get a low weight or a weight which is close to zero. Okay, so this is actually, you see the advantage of this one by one convolution, that it is actually choosing which of these 32 values is more important. And if I do convolution with one such filter, 1 cross 32, I get one output, right? If I do with two such filters, I will get two outputs. And if I do the same convolution with 20 such filters, then of course I will get 20 such outputs, right? So I can control how many or what should be the depth of output volume if I want to do that, right? So let's do some more discussion on this, right? And by the way, this idea of one by one convolution, it was not introduced in Inception V1, right? There was a paper which was called Network in Network, NIN, right? This one, which introduced this concept of one by one convolution, and it was borrowed in this Inception architecture from this particular study, right? So as I told you, that we already know that if we want to reduce the spatial dimension, we use pooling, right? For example, we want 28 by 28 to become 14 by 14. So we can use pooling with a stride of 2. So we can reduce the spatial dimension by a factor of 2. If we want to reduce the depth, then we have this, which is called one by one convolution. So suppose I have 28 by 28 by 192. Now I am a bit concerned about this number 192. I say, okay, let's reduce the depth. Okay. So what I do one by one convolution. So my filter is actually 1 by 1 cross 192. Okay. And how many filters I'm using? 32 such filters. So what will happen? My output would be 28 cross 28 cross 32. Okay, so it means now I have 192 values in the depth, 192 values in the filter. I will take a weighted combination of these values, right? So out of these 192 values in the depth, if some values are important, they will get a high weight. If they are not important, they will get a low weight, right? And I'm using 32 such filters. So with that, we'll expect that we are actually picking up some useful information, right? Please don't think that when I reduce 192 to 32, so I'm losing a lot of information. Yes, we are losing, but we are doing it smartly. We are not simply throwing away values. We are taking a weighted combination. So if something is useful, it will be actually combined, and it will be represented in a more compact form rather than simply throwing it away. Okay, so now with that, let's get back to our Inception from where we started our discussion, right? That you see, we said that on the same input volume, we'll be applying multiple convolutions, 1 by 1, 3 by 3, 5 by 5, and max pooling. But since this dimension is very, you can say, high. So applying multiple filters can actually increase the computational cost. So what we'll do in this case is that we'll introduce additional 1 by 1 convolution before 3 by 3 and 5 by 5 convolution. And why we are doing that? The reason is that whenever we are trying to reduce the complexity of a model, right? So in a model, basically, there are two key operations. One is multiplication, other is addition, right? Because you take the dot product. So if you know from hardware perspective, if you have to implement something in the hardware, so addition is actually a simple operation, right? It does not cost much if you want to implement it. On the other hand, multiplication is a costly operation, right? If you want to implement it in the hardware or assembly language. So basically, number of multiplications is considered a good indicator of complexity. So our objective is that if we can reduce the number of multiplications, that actually means we can reduce the computational complexity, right? Because this is the most critical operation. Okay, so now let's see an example how we can exploit 1 by 1 convolution to reduce the computation, or in other words, to reduce the number of multiplications, right? Now please see this discussion carefully because this is important. We have an input volume of 14 by 14 by 480, right? You see this is a big number. We do convolution with 5 by 5, 48 such filters. So the output we get is 14 by 14 by 48. Okay. When this is the filter, so actually this filter is 5 cross 5 cross 480, right? Because the depth of the filter is always equal to the depth of the input. Now, let's see how many multiplications are involved in going from this volume to this volume, right? Previously, we have been focusing on size of volume and number of parameters, right? That we already know. Size, you can compute directly or using the formula. And number of parameters is actually this plus the number of filters, okay? So that we already know how to compute parameters, how to compute size. Now there's an additional thing that we are computing, that is number of multiplications. Okay, now how do we compute the number of multiplications? Okay. You see, your filter is 5 cross 5 cross 480. So when I put my filter here on this region, right, this is a 5 by 5 filter. Okay. So how many multiplications I do for one convolution? For one convolution, I do these many multiplications. If this is not very straightforward for you, just think of a 3 by 3 by 3 filter. Okay. When you do convolution with a 3 by 3 filter, how many multiplications are there? You have 27 values. You have 27 values in the filter and 27 values in the image. So there are total 27 multiplications, right? So similarly, you do those multiplications and you compute one value. So computation of one value requires 27 multiplication. Then you move your filter to the right. You compute the next value, which again requires 27 multiplication. Then the third value, fourth value, and so on, right? So it means when you are making this output, in order to compute this one value, okay, how many multiplications are required? 5 into 5 into 482. For the second value, again you need 5 into 5 into 480. For the third value, again same number of multiplication, and so on, right? So in order to compute one value, you need 5 into 5 into 480. And how many values you are computing in total here? How many values are here? These many values, right? So it's very simple. How can you compute the number of multiplications in going from one volume to another volume? You see how many multiplications are involved in computing one value. Okay, this is for one value. And how many values you are computing? You are computing the same values which you have in the output volume, which is actually 14 into 14 into 48. Okay, so this is basically the total values you are computing, okay, which you can see from the output volume. And if you multiply them, the number you get is around 113 million, right? So you have the exact number in the slides. Let me flash it at 112.9 million, right? So this is the total number of multiplications you need if you use this, okay? Now, this is a very big number, right? 112 million. So, and this is only one layer. So you can think that in the subsequent layers, when you have more filters, more operations, so the total number of operations would exponentially grow. So in order to reduce it, we introduce 1 by 1 convolution in the network. And this 1 by 1 convolution is actually called the bottleneck layer. Okay. why do we have this name bottleneck? If you see bottle like this, so you see this neck of a bottle is actually the thinnest part. Okay, here you see you have a diameter which is quite wide, but the diameter of the neck is very small. Okay, so same is the case with this network, right? We are introducing a new layer. So you see here you have 480, which is quite a deep depth. Similarly, you have 48 here. Here you have a very small depth, right? So you have like a very shrunk volume. The depth has shrunk a lot, right? So that's why it is similar to the thinnest part. It is like the thinnest part in the network, which is similar to the thinnest part in a bottle, which is called neck of the bottle, right? So that's why there's this terminology bottleneck layer, which actually is used to represent one by one convolution. Okay, now what are we doing now? Let's get back there. Here you see from 14 by 14 by 480, we were going to 14 by 14 by 48. So if you ignore the central part for the time being, you see this number and this number. They are exactly the same which we are having previously, right? Input was 14, 14, 480, output was 14, 14, 48. But there in the previous slide, we were going from input to output in one single step, which was costing us 113 million operations. Now we are doing the same thing, but we are doing it in two steps. Okay. In the first step, we introduce a one by one convolution. So it means the filter is one by 480, but we keep this number very small. So we have kept it to 16. So what will happen? My intermediate layer will be 14 cross 14 cross 16. Now you see this is a very small number. Now when you will design the filter for the next layer, so here this depth would be actually 16. Okay, so previously when you were doing the depth of a 5 by 5 filter was 480, due to which not only number of parameters was increasing, but number of multiplications was also increasing. Here we have done something smart. We introduce an intermediate layer where we have a very small depth, like 16, which is a very small number when you compare it to 480. So when you will do the next convolution, the depth of this 5 by 5 filter will be only 16, which will eventually result in a very fewer number of multiplications. Now let's do the exact calculation that now how many multiplications we'll have in each step. Since we have two steps, so first we compute the number of multiplications here. Okay. So as I told you, how do we do that? First, you see how many multiplications are required to compute one value. Okay, and that is actually same as the size of the filter. So for one value, you need 1 into 480 multiplications to compute one value. How many values we are computing? We are computing these many values, which is actually the size of output volume. So we are computing 14 into 16, right? So if you multiply them together, you get something like 1.5 million. Okay, so this is basically step one. Now step two, which is this one, right? How many multiplications we do in order to compute one single value here? Okay, so the size of the filter is 5 cross 5 cross 16. Means in order to calculate one value, the number of multiplications is 5 cross 5 cross 16. And how many values we are computing total? Total we are computing 14 into 14 into 48. So total number of multiplications is, and if you compute, it is, I don't remember, I think it was something like 3.8 million. So if you add them together, step one and step two, you add them, you get 8 plus 5 is 3, and this is 5.3. This is 5.3 million. Okay, so you see previously we were getting 113 million. Now the input and the output have the same volumes, but now the number of parameters, or sorry, the number of multiplications from 113 million, it has reduced only to a little more than 5 million, which is a huge gain. Okay, and how did we achieve it? That since this depth was very large, so instead of using a 5 by 5 filter, we use it with a 1 by 1 filter. And we keep the depth of this intermediate layer very, very small. That's why it is called a bottleneck layer. So next, when you do convolution with 5 by 5, so in the previous example, the filter was actually 5 by 5 by 480, which was causing a lot of computation. Now we have smartly reduced this depth to 16. So the filter is only 5 by 5 cross 16. So when the depth is lesser, of course, you will have fewer number of multiplication, right? So these are the exact calculation. Yes, I think they are the same. Okay, now let's do one more example of same so that you understand what actually is going on. Okay. So in this case, again, we are not doing any, you can say, one by one convolution. There is no bottleneck layer. So let's see what is the number of multiplications in this particular example, right? So in this example, again, what is the size of the filter? Size of the filter is 5 cross 5 cross 192. Okay. It means in order to compute one value, this is the number of multiplication. And how many values we are computing? We are computing 28 cross 28 cross 32. Okay, so this total number, you can do that, right? Whatever this number is, it will be more than 100 million, right? So I don't remember exactly. Yeah, it is actually 120 million. Now let's introduce a one by one convolution in between. Okay, so this is basically a new intermediate layer or the bottleneck layer we have introduced. So what we are doing here, we are using one by one convolution and 16 filters. Okay, so how many multiplications would be there? One, to compute one value, you need 1 into 192 multiplication. How many values you are computing? 28 cross 28 cross 16. So it is 28 cross 28 cross 16, right? So this is step one, going from input to the intermediate volume. Now for the step two, what is the size of the filter? The size of the filter is 5 cross 5 cross 16. Okay, this is the number of multiplications you need for one value. How many values you are computing in total? This is 28 cross 28 cross 32. You add them together, okay, and you get something which is like 12.4 million. So you see from 120 million, now you are around 12 million, which is the previous case was actually 10 times more than what you are getting here, right? So this is actually what bottleneck layer does, that it can greatly reduce your number of computation, right? Okay, now with that preamble, we are now in a position to go back to the Inception module, right? So you see, when we started a discussion, we said, okay, whatever is the previous layer you have, right? So instead of having one single convolution, this is from the previous volume. So you are applying multiple convolutions with different filter sizes, and you are also doing pooling, and then you are actually concatenating the outputs of these different operations, right? So this is actually the naive version of Inception, which does not include bottleneck layer, right? Please note that one by one convolution you see here, this is actually not a bottleneck layer, right? This is just a convolution with a one by one filter size. When we introduce bottleneck layers, we'll be introducing those before these convolutions so that we have a shrunk representation and we can limit the number of multiplications, right? So this is the Inception module with bottleneck layers where the objective is to control the depth, right? So here what we are doing, you see, before directly applying 3 by 3 convolution, we first introduce a 1 by 1 convolution so that because this will have some significant depth. So with this 1 by 1 convolution, we can actually reduce depth. Okay, we can control depth to whatever we want, and then we apply 3 by 3 convolution, right? Same is the case here. Just like I showed you in the previous example, directly applying 5 by 5 convolution on a big depth, maybe a depth of like 480, it will be very expensive. So first you have 1 by 1 convolution, maybe you can reduce this depth from 480 to 16, and then you apply 5 by 5 convolution, right? And here you see the 1 by 1 convolution is after pooling. Why? Because pooling layer does not have any parameter. So first we do pooling, and then we apply 1 by 1 convolution, because this pooling actually will not have any impact on the depth, right? Pooling does not have any parameter. So once you have applied the pooling, afterwards you can control the depth with a 1 by 1 convolution. So this is just again a visual illustration of what is going on, maybe in terms of volumes, right? So you have a 1 by 1 convolution before 5 by 5 and 3 by 3. And then you also apply a normal 1 by 1 convolution. So you see, these are the different outputs which are concatenated together. Okay, and eventually this becomes the input for the next layer. This is yet again another representation, right? But an important aspect here is that you see this part, that we are doing pooling, but we are doing pooling with padding and a stride of 1. Okay, so you see, this is a slightly strange kind of pooling that let me maybe explain it on the board. That normally when you do pooling, if you remember that the window used to be 2 by 2 and a stride was 2. Okay, and there is no padding in pooling. Okay, so if we do this setting, so what happens with pooling is that if this is say n cross n, so this is reduced to n by 2, n by 2. But the pooling you see in Inception is a bit different. We say 3 by 3 pooling with padding, and the stride is actually 1. So if you do pooling with these parameters on n by n, then eventually you actually end up with n by n. You do not reduce spatial dimension with this pooling. Okay, and this is the reason that you see, if this pooling was reducing spatial dimension, then we would not have been able to concatenate them. Okay, for example, if all the filters are like say 50 by 50 and pooling is giving you 25 by 25, then it is not possible to concatenate these two, right? Because for concatenation, all the matrices have to be of the same dimension, right? So then why are we doing this pooling? Because this pooling is actually simply picking maximum values within a neighborhood and replicating that maximum value without reducing the spatial dimension. And later we have a 1 by 1 convolution, which acts as a weighted combination. So it can actually choose which of the values it wants to keep and which are the values it wants to discard, right? So this is important, that when you have this pooling within the Inception module, this pooling is not reducing the spatial dimension, because if here we reduce the spatial dimensions, we will not be able to perform concatenation, right? Because when you are concatenating these different outputs, all of these have to be same spatial dimension, right? Otherwise, we'll not be able to concatenate them. Okay, so just keep that in mind. What is Inception module? I'll come back to that in a while. But there are two important aspects which are related to Inception, which we'll introduce for the first time. We'll discuss them, and then we'll put all these pieces of information together to see the complete Inception module, right? So there's a new type of pooling which is introduced in this Inception, which is called global average pooling, right? It is actually, you can say, a very severe type of pooling, because normally pooling would reduce your spatial dimension by a factor of 2 or 3 or something, right? But what it does is that if you have an input of H cross W cross D, right? Or maybe you say 10 cross 10 cross 3. When you do global average pooling, it will shrink it to 1 cross 1 cross 3. Means whatever this number is, it will become 1 and the depth is preserved. Now, how does it work? It's a good idea to see this example. We have here a volume of 6 cross 6 cross 3. Okay, so you have this purple 6 by 6 matrix. Okay, similarly, you have this channel 1, channel 2, and channel 3. So global average pooling says that in each of these matrices, you just keep its average. Okay, so I take the average of all the values in channel 1. In other words, all the purple values, and I get one number. So this whole 6 by 6 average is represented by this one number. Similarly, I pick this channel 2, in which I have 36 values. So the average of those 36 values is here, this one. And similarly, in the third channel, the average of 36 values is this one. Okay, so it means from every channel, I am just keeping the average. So whatever my dimension was, I get eventually 1 cross 1 cross D. So you see, it is a very severe type of pooling, that from 6 cross 6 cross 3, we are coming down to 1 cross 1 cross 3, right? So all of a sudden, you are just keeping the average. Now, what is the advantage of this? Because it looks very severe, that you see, if I have this volume and I am using a fully connected layer, that it means I need to connect everything with, say there are 1024 neurons in the next layer. So it means everything here is connected with all these neurons. So the total number of connections would be, I will flatten it, this into 1024. On the other hand, when we are doing global average pooling, so from this 7 by 7 matrix, I am just keeping its average, which is one number, right? So I just keep its average. Similarly, from the second channel, I keep average, which is one number. So I'll have actually 1024 numbers, right? Because my volume was 7 by 7 by 1024. I apply global average pooling, I get 1 by 1 by 1024, right? So you see, by applying global average pooling, we are not introducing any new parameters because we are just computing the average. We just compute the average of all the values in a given channel, and then we get one single scalar value. So there are no actually parameters involved, right? Because we are simply having the mean of every, you can say, feature map. Okay. So now with this, basically you see putting these pieces together, which I'll show you subsequently. So in 2014, the Inception V1 actually was submitted to the ImageNet competition, where it got the first place, right? And how was the model built? You see, we have seen Inception modules, which is actually 1 by 1, 3 by 3 pooling, right? So now this is one building block. And with GoogleNet or Inception V1, you have 9 Inception modules stacked together, right? Means Inception module 1, then second, and then third, and so on, right? So you have 9 modules. And eventually you have this global average pooling layer. So the total number of layer in this network, if you count them, it comes out to be 22, of course, excluding the pooling layers, right? And the error rate it reported was quite low, which was 6.6%, right? From the perspective of number of parameters, right? You see, if you remember LXNet had 60 million parameters, right? Now, from 60 million, this number was reduced to 4 million in you can say GoogleNet or Inception V1, right? So this was actually a screenshot which shows the performance or the error rate of different systems which were submitted to the 2014 competition, right? So LXNet was always used as a benchmark, right? Because it was the first winner of this competition, which was using CNN, right? So here you can see this Inception V1 was, you can say, reporting the lowest error rate in 2014, right? Now, this basically actually gives you, you don't need to understand it fully, right? But I'll just give you some key aspects, right? So you see, this is one Inception module, which we have seen in detail. Okay, and this is repeated, right? 2, 3, 4, 5, 6, 7, 8, 9 times it is repeated. Okay. Now, what you see here, right? So you also have these blue parts. This is the normal convolution, which you have in a normal CNN, right? You have a volume, you apply convolution. So you see, it is a mix of different things. You have normal convolution. You also have normal max pooling, right? This red one is normal max pooling. So this is actually in the beginning, this part is quite conventional. Okay, and then you have these Inception module, which is repeated 9 times. Okay, there's one new piece of information, which you see these two branches. Again, this was a new concept that was, you can say, employed in this architecture, which is called auxiliary loss. Now, what is this? That you see, since it's a very deep network, so if you take only this part of the network till here, it should still be learning something useful, right? So if we do classification only with this part, we should not get something rubbish. We should be getting something which is somewhat useful, right? So we have a branch here, which is actually computing the loss. Similarly, we have another branch here, which is also computing the loss that, okay, what is the loss if I only use this part of the network for prediction? And of course, you have the final loss. So the total, you can say, loss is computed as a weighted combination of the auxiliary loss and the final loss. So you see, this is your final loss, right, which has a weight of 1. And these are your auxiliary loss 1, auxiliary loss 2, which has a weight of like 1 by 3, right? Because we cannot give it the same weight because this is in the middle of the network. So basically, this actually ensures that the initial layers are also learning something useful. Okay, when you have a weighted loss like loss 1 plus 0.3 auxiliary loss 1 plus 0.3 auxiliary loss 2. So you see you have some weight for these loss. So it will try to learn those features that if I only had this part of the network, the performance of the network is still something acceptable, right? It is not too bad. So this is like preventing overfitting and itself like a regularization, right? So this was Inception V1, right? Maybe we can take a pause now and we discuss after a break. Okay, now now we have, after having seen Inception version V1, right, we'll now move to the next version, which are actually improvements on the existing model, right? So which are V2 and V3, right? So if you actually go through the literature and the tutorials which are available, so you will find some contradicting discussions related to what is the difference between V2 and V3, right? Different blogs will present them differently, right? Some of the reviews will think that they are almost the same thing with some minor differences and so on, right? And even if you go through the paper, so they're not very easy to follow, right? So it was actually the paper of Inception V4 where authors clearly and explicitly state the differences between these different versions, right? And the text you see on this slide is actually taken from the paper of Inception V1, which is actually explicitly telling that what are the key differences in these different models, right? So Inception V1 or GoogleNet, right? So GoogleNet or Inception V1, it is actually the same thing, right? But as I told you, when this model was introduced in 2014, they only called it Inception, right? Because in advance, you don't know that there would be a second version. So it was called Inception, right? But at a later stage, this was given the name Inception V1. Now, well, then what is V2 and V3, right? So authors say that the Inception architecture was refined in various ways. First, by introduction of bash normalization, right? And which they are calling V2. So it means that V2 is actually introducing bash normalization. And then they say later by addition of factorization idea in the third iteration, which they are calling V3. So in V3, the main focus is on factorization, which I will tell you in a while that what is actually factorization, right? But this is very important because if you will read some of the blogs or tutorials, so uh, they can be very confusing, right? So just remember that Inception V2 is about bash normalization, right? Which we have already seen, right? Bash normalization. And Inception V3 is about factorization, which we'll see in detail in a while, right? So this is basically the paper which introduces Inception V2. And as you can see in the title, it is talking about bash normalization, right? Again, it has all those details which we have seen more or less, that the idea of batch normalization was to speed up training by normalizing the outputs of different layers, right? Just like we normalize the input layer, we also normalize the different outputs of the different layers. So by normalizing those activations, we can actually speed up our training, right? Now, this is actually the paper of Inception V3, right? The title is Rethinking the Inception Architecture, right? Means some major changes in how convolution is performed. And this is again, the paper, it's relatively easy to follow as compared to the previous version, right? So you can go through it, right? Okay, so the key idea of Inception V3 is factorizing convolution, right? Now, what does factorization mean? Let's suppose this is a 3 by 3 filter. Okay, and if you remember, this was the first filter that we saw when we were developing the idea of convolution, right? This is an edge detector. And if you are familiar with its name, it is called a Sobel edge detector, right? Even if you don't know its name, it's okay, right? This is a filter which can detect edges in an image, right? Now, you see it's a 3 by 3 matrix. So total there are 9 parameters. Okay. Now the idea is that I can split this convolution into two convolutions. That first you perform convolution with a vector of 3 cross 1, you will get some output. And then you perform convolution with this 1 cross 3, and we expect that we get the same thing which we were getting with this 3 by 3 filters, right? So here you have 9 parameters, and here the total number of parameters is 3 plus 3, which is 6. Okay, so from 9, we have reduced the number of parameters to 6. Okay, and just to convince ourselves that we can actually get the same thing, let's take an example and let's apply convolution on it, right? Let's do a numerical example, okay? So suppose we have an input which is like, say, 2, 2, 2, 3, 3, 3, 4, 4, 4, right? So I just take a small patch, which is 3 by 3, right? This is my input. Okay. And we do convolution with the 3 by 3 filter, which is -1, -2, -1, 0, 0, 0, 1, 2, 1. Okay, so we want to see, okay, what is the result of this convolution? Okay. So once you do convolution, you superimpose this on top of the image. You take, you multiply the respective elements together. So you get -2, -4, -2, first column. Then second column is like 0, 0, 0. And the third column is 4 plus 8 plus 4. Okay, you just multiply with the filter values. So eventually you get, this is -8, 16. So eventually you get 8. Okay, so the output is 8. And the filter has 9 parameters. Okay, now on the same input, which is this 3 by 3 matrix, let's apply a factorized convolution, right? So we keep the input same. This is our input. Okay, and we first apply convolution with this 1 to 1. Okay, now our filter is 3 cross 1, means 3 rows and 1 column. Okay, so what we'll do, we'll again superimpose this filter, maybe first on the first column, then second column and third column, right? Because we'll move in this direction. So when I do convolution of this by superimposing it on the first column, so I get 2 plus 4 plus 2, right, which is 8. This is the first value. Then I superimpose my filter on the second column. So I get 3 plus 6 plus 3, which is 12. Okay. And then when I superimpose it on the third column, so I actually get 4 plus 8 plus 4, which is 16. Okay. So what I get as an output is 8, 12, 16. Right. Why I'm getting 3 values? Because you place the filter here, then you move it to the right, then right. So against each you are getting one value, 8, 12, and 16. So this is the output of this particular convolution. Now on this, we again apply convolution, and now our filter is -101. Okay. Now what it does, you multiply the respective values together, you add them, so it will be -8 plus 0 plus 16. So eventually we get 8. Okay. And now you see what was the answer we were getting with the 3 by 3 convolution? It was 8. And here again we are getting 8. But in this case, we have 6 parameters, right, as compared to 9 parameters. So you see, by factorizing convolution, we arrive at the same output, or you can say we'll arrive at the same feature map, but the number of parameters is reduced. And once you are reducing number of parameters, then of course you are also reducing the number of multiplications. Okay, so you see, this is basically the same example which we solved. You have a 3 by 3 convolution, you get 8. You split this convolution into, or you factorize this convolution into 2 separate convolutions. First, by this 3 cross 1 vector, you get this as output, and then on this you apply convolution with this 1 cross 3, and you get the same output with lesser number of computation, right? So, and then you can say visual illustration, which tells you that rather than directly going from here to here, you can actually split the convolution into 2 steps, where you have an intermediate volume, and then you apply another convolution. So you can end up with the actually the same output, right, which we numerically also saw. Now let's see how much actually we are gaining. We have already discussed from the perspective of parameters that it is straightforward that we have 6 parameters rather than 9 parameters. But let's see how much do we gain in terms of number of multiplications, right? Let's see what are we gaining. Okay, so here, suppose this is your input, which is like 5 cross 5. This is your filter, which is 3 cross 3. Okay, so we are doing convolution. I put my filter here. Okay, and I have 9 multiplications, I get this value, the first value. Then I move my filter 1 position to the right, and I have again 9 multiplications, so I get the second value and so on, right? So since we are not doing any padding, so the output is actually 3 by 3. Okay, so in order to compute one value, we have 9 multiplications. Okay, in order to compute one value, how many values we are computing? 1, 2, 3, 4, 5, 6, 7, 8, 9. Total, we are computing 9 values. Okay, so the total number of multiplications is 81. Okay, you have the computations in the slide as well, that there are a total of 81 multiplications in this operation, where we are applying a 3 by 3 filter on an input of 5 cross 5 with a stride of 1 and no padding. Okay, if you can do directly, it's good. If you cannot do it directly, you always have the formula n minus f plus 2p by s, the same which we have used many times. You can plug in the values and find out what would be the size of the output. Okay. Now we split this convolution just like we did in the numerical example. So first we do convolution with a 3 by 1 filter, which is this one. Okay. So we do filter of this 5 by 5 image with this 3 cross 1 filter. So as an output, we get a matrix which is 3 cross 5. Okay. Now let's see how many multiplications we are doing here. So in order to compute one value, the number of multiplications is 3 cross 1, that is 3 multiplication. How many values we are computing total? 3 into 5, 15, right? These are 15 values, 1, 2, 3, 4, 5, and so on. So the total number of multiplications is 3 into 15, which is 45. Okay, so still here we have 45 multiplication. Now on this, we are again doing convolution, and this time the size of the filter is 1 cross 3. Okay, so let me just write it, 1 cross 3. So the total number of multiplications I need in order to calculate one values is 1 cross 3, which is 3. And how many values we are computing in total? 9 values. So it means total number of multiplication here is 27. So we have 2 steps. If we add the multiplication of 2 steps, 7 plus 5 is 2. And this is 7. Okay. So from 81, we come down to 72. Right? This might not appear a very big gain, right? But think in terms of millions, right? And here the filter size was small, input was small. So when the input size is big, and we are talking about numbers which are in millions, so this actually would be a big gain, right? So the summary is that using spatially separable convolutions, you can reduce the number of parameters, you can reduce the number of multiplications, right? But still, you will see that this is not a very popular idea in deep learning community, right? It was proposed in Inception V3, people use Inception V3, but other than that, this idea is not very popular, right? And the reason is that when you split or factorize the convolution, the results may be suboptimal, right? Because it is easy to learn a 3 by 3 filter, achieving some effective feature, as compared to learning a combination of 1 by 3 and 3 by 1, which is actually learning the same feature, you see, because this is relatively easy. You have one matrix to learn, which is giving you some useful feature. If you want the same feature through a combination of 2 different filters, then you can guess that may not be very easy to actually learn, right? That's why it is not very popular, but anyways, it was used in V3, so we can actually discuss it, right? So coming back to V3, that was an introduction to how factorized convolution work. Now, how Inception V3 exploit this idea of factorizing convolution, right? So there are different ways they have used it. You see, just like we replaced a 3 by 3 convolution with 3 cross 1 followed by 1 cross 3, right? So similarly, if you have, a 5 by 5 convolution, okay, so a 5 cross 5 convolution can be replaced by a 3 by 3 convolution followed by another 3 by 3 convolution. Okay, so you can actually numerically take a matrix, apply 5 by 5 convolution on it, or first apply 3 by 3 and then on the output again apply 3 by 3. So you will end up with one, you can say, same value, right? You can do it with numerical values just like we did it with the, you can say, 3 by 3 filter. So if we see how much we are gaining in this case, so in case of a 5 by 5 filter, total number of parameters is 25. If we replace this 5 by 5 by two 3 by 3 filters, the total number of parameters is 18, 9 plus 9. Okay, so the total reduction is around 30%, 28% to be precise, right? That from 25 parameters, you are going to 18 parameters, right? So the reduction is around 30%. Okay, now see how this is exploited in the network. Okay, if you remember Inception V1, what did we have? We have this thing, okay, and we had this thing, and this was actually a 5 by 5 convolution. Okay, so what they have suggested that this 5 by 5 convolution, which was there in Inception V1, we can replace it by two 3 by 3 convolution, right? So instead of one 5 by 5, you have two 3 by 3. Otherwise, this whole block is same as what we have seen in Inception V1. Okay, so this is one change that they have suggested. What is that change? Replace the 5 by 5 convolution in Inception V1 with two 3 by 3 convolution. And they call it Inception Module A. Why A? Because there is a B and a C coming up as well, right? Which are more or less similar, but the amount of factorization is actually different. Okay, now extending the same idea, you see, as we discussed earlier, just like you can factorize a 5 by 5 convolution, you can factorize a 3 by 3 convolution into two convolution, 3 cross 1 followed by 1 cross 3. And how much we are gaining in this case? In a 3 by 3 convolution, you have 9 parameters, right? And if you replace it with two convolutions, the total number of parameters is 6. So that again, the reduction is around 33%. Okay, that from 9 you are actually going to 6. Okay, now you see this is again the same, you can say inception block, but now you see a lot of factorization. And just assume that this n is actually 3. Okay, so if n is 3, so actually it is 1 by 3 followed by 3 by 1. So this is actually the 3 by 3 convolution which was factorized. Okay, so it was 3 by 3 convolution. If you come here, see, this is, it has been factorized into 1 by 3 and 3 by 3. And this leftmost was actually a 5 by 5 convolution. In module A, we replace 5 by 5 by 3 by 3 and 3 by 3. Now, each of these 3 by 3 can be further split into two steps. Okay, so you see, this is actually 1 by 3, 3 by 1. And both of these become 3 by 3. Similarly, this is 1 by 3 followed by 3 by 1. And both of these become 3 by 3. And these two 3 by 3 actually are same as, you can say, 5 by 5. So you see, from 5 by 5, we split into 3 by 3, and then each 3 by 3 is split into 3 by 1 and 1 by 3. So it is basically, you can say, an extreme case where everything has been factorized. Okay, and this particular case is called Inception Module B, where you have too much of factorization, means every possible thing that could be factorized has been factorized. Okay, and there's another third, you can say, possibility, which is called Module C, where this part, which was 3 by 3, it is factorized. Okay, and this was 5 by 5, in which the first one is kept at 3 by 3, but the next 3 by 3 is split into, you can say, two convolutions, right? So you see these are actually different combinations of how you can factorize. So you can choose some other combination, right? Maybe you can split this one and keep the top one intact, right? It's your choice, but this is what was kept in the standard Inception V3. So now you have a module A, module B, module C. In module A, what we are doing, we have this 5 by 5 factorized into two 3 by 3. In module B, we have almost everything factorized to the level it could be. And in module C, we have this factorization and only one factorization of 5 by 5 into 3 by 3, and the subsequent 3 by 3 is factorized into two convolutions, right? Now we have three different types of modules, and another difference with previous Inception models is that in Inception V1 we had two branches or two auxiliary classifier, right? And in case of Inception V3, we just have one auxiliary loss. Okay, there's only one branch. So this is the complete architecture. Again, you don't need to memorize it. It's just for discussion. So we'll only focus on the key aspect. The input is 299 by 299 by 3. So you see, initially you have 5 blocks of module A, right, which we discussed. Then 4 blocks of module B, and 2 blocks of module C. Okay, and in between you have this branch which you see here. This is the auxiliary classifier. So you compute the loss here and you add it to the final loss. And of course, in between you also have the conventional layers, the convolution and the pooling, just like you have, right? In total, the total number of layers in this architecture is more than 40, right? 42 to be exact. So this was actually a popular architecture which is available, but you can guess that computationally it's quite expensive. You can actually load it and do model.summary to find the total number of parameters in this particular architecture, right? So, but this is a famous architecture that you will find in many different studies, okay? So I'll not be covering this Inception V4, right? If anyone is working or doing research on it, so they can actually go through this paper I have mentioned here, right? So the key idea of this, I will tell you, but since we have not seen ResNet, we'll see ResNet in a while. But once you see ResNet, so you can guess that this Inception ResNet actually combines the features of Inception as well as ResNet, right? So, but we'll not be discussing it in the class because else it will take a lot of time. So we'll just see one more model in the Inception family, which is the exception. But before we see this, if you have any queries from Factorized Convolution, you can let me know, right? Then we see this last model in the family, which is exception. Thank you. Okay, so the last model in this family is exception, right? And exception actually is like extreme version of Inception, right? So you pick E from here and maybe X from here, and then this part from here. So you combine them, EX and this part. So you end up with this name, which is called exception, right? Which is extreme version of Inception, okay? So in order to understand, I'll just do a numerical example so that you get the idea. The key idea of exception is something which is called depth-wise separable convolutions. Okay, now what are these and why they are useful? I'll be telling you in a while. So in order to understand, let's assume you have an image, right? Colored image. So you have some values here. Okay, you have 3 channels, red, green, and blue. So maybe this is the blue channel. Then you have the red channel. And finally, you have the green channel. And say this is like 64 by 64 by 3. Okay. Now, when we do convolution of this, okay, with the 3 by 3 filter, 3 by 3. So we know that the filter depth would also be 3. It means I have a 3 by 3 filter, which I will apply on the blue channel. I will have a 3 by 3 filter, which I apply on the red channel. And I have a 3 by 3 filter, which I apply on the green channel, okay? So applying this filter on the blue channel will give me something. Applying this on the red channel will give me something, and applying it on the green channel will give me something. We add all of these together, and then we get one single feature map, okay? Why we get one single feature map? Because whenever I'm doing convolution, I'm placing my filter here on the red channel, green channel. So we have, you can say 9 multiplications here, 9 here, 9 here. So I get 3 values, say A, B, and C. I add them together and then I get one single value here. Similarly, when I move my filter 1 position to the right, I have again 27 multiplications. I add all them and I get this number. Okay, this is the conventional way of how you apply convolution. Now, in this case, the convolution would be slightly different, right? And what would be that difference? That whenever you are applying convolution on the channel separately, so you will not be adding these, right? Instead of adding these, right, you have one output from red, I call it red output, and one from, say, sorry, it was blue. So output from blue, then you have output from red, and you have output from green. Instead of adding them, what we do is we concatenate them together, right? So you will have basically something again which will have a depth of 3. So you see we are separately applying convolution on each of the channels, and we are not adding their resulting output. We are simply stacking them. In this case, the depth was 3. This depth can be 30. So it means when you will stack, you will get 30, a depth of 30. And normally after this, there is a common operation that since this depth can grow, so in order to control this depth, you can always use a 1-by-1 convolution or pointwise convolution to keep the depth to the number which you desire, right? So this is the key idea of depth-wise separable convolution, that instead of adding the outputs of different channels, we keep them separate, right? So now let's go back to our lecture slides and then discuss from there how actually things are working, okay? So as I told you that the key concept of exception, which actually stands for extreme inception, is depth-wise separable convolution. If I have a volume where I have a depth of say 1, 2, 3, 4, then my filter also has a depth of 4. Okay, and when I apply this filter, I add the outputs of all these and I get one feature map. If I apply 2 such filters, I will get 2 feature maps. Okay, but in case of depth-wise separable convolution, what are we doing? My depth is 1, 2, 3, 4, and filter is also 1, 2, 3, 4. This small green window is actually the filter. So when I apply these filters on each of the channels, I keep their output separate. So you see how many outputs I have? 1, 2, 3, 4. Previously, you were actually adding all these purple blocks and you were getting just one 2D matrix, right? But now we are keeping them separate. We are not adding them together. So this is basically what is called separable convolution. And after that, normally what we do, we use a pointwise convolution, okay? And we can control the depth to whatever we want. Okay, so maybe this will better illustrate the idea that this is our input, okay, which has say 1, 2, 3, 4, 5 channel. So on each channel, you separately apply convolution, right? Channel 1, channel 2, channel 3, and you will get same number of outputs as you have channel. So you can concatenate them together, right? So you see here the depth was 5. Since we separately apply convolution, we don't add them. So here again the depth is 5. So you see depth has not changed because we are not adding them together. Previously, all of these 5 were added and you were getting just one single feature map. And after this, suppose this depth is 5, you say, no, this 5 is a big number. I want to reduce it to 3. So you can always do a 1-by-1 convolution, okay, where just like we saw a little while back with 3 filters. So you can control the depth to whatever number you want. So if we summarize, so we say in exception, we have 2 key operations. First is the depth-wise convolution or depth-wise separable convolution, where we apply convolution separately on each of the channels of the input volume. We don't add them together. We have multiple outputs, we stack them, and then we apply a pointwise convolution, which is actually a 1-by-1 convolution to keep or to change the depth to whatever number we want. Now let's see what actually we are gaining here, okay? So again, you must have guessed that the key idea is to reduce the computations, right? So let's first see a standard convolution. Okay, so our input is 7 by 7 by 3. This is our filter, which is 3 by 3 by 3. So what you do is that this is your first channel. You multiply it with this first channel. Then this is your second channel. You multiply it with the second channel here. And then this is your third channel, right? So you have 27 multiplications. You add them together, you get one single value, which is this one. Okay. Then you move the filter one position to the right. Again, 27 multiplications, you get the second value, and finally you get the last value. Okay. So since in this example, we did not do any padding. So actually from 7 by 7 by 3, we end up with 5 cross 5 cross 1. Why 1? Because we are adding all the values together. Now, if instead of one such filters, suppose I have many such filter. So if I have 10 filters, the depth of output would be 10. If I have 100 filters, the depth of the output would be 100, right? This we already know from our previous knowledge, that the depth of output is always equal to the number of filters, okay? So in this case, suppose if I have 128 such filters, so the depth of the output would be 128, right? So this is basically the standard convolution with which we are already familiar. Now what we'll do, instead of applying the standard convolution, we will split this convolution into, you can say, different channels that will separately apply convolution on a channel and will not add the outputs, we'll keep them separate. Okay. So now you see, basically what we do, that this 3 by 3 filter, okay, we apply on this part, which we have highlighted by the, you can say, orange color. Similarly, on the second channel, we apply this filter separately, and this green part we apply on this part. Okay, so we have, you can say, you can treat them as 3 different filters separately applied on each channel. And previously we were adding all these values together, so we were getting only depth of 1. Now we are keeping them separate. Okay, we are not adding them. So you see, it means now in this case, my output would be 5 cross 5 cross 3, because since I'm not adding the outputs together, so whatever was the depth here, I apply separately on each channel, and the depth of output is also 3. Okay, so from 7 by 7 by 3, after depth-wise separable convolution, my output is 5 cross 5 cross 3. It means I'm actually not losing anything on the depth. Now what we'll do, now we will apply a 1 by 1 convolution. Okay, so you see, this is a 1 by 1 filter, and the depth of this filter is same as depth of input. So if I apply a 1 by 1 filter on this, I will get a 5 cross 5 cross 1, right? Because I'm applying one such filter. This 1 by 1 convolution is exactly the same, which we saw a little while back. And instead of one such filter, if I do 1 by 1 convolution, say with 128 different filters, my output would be 5 cross 5 cross 128. So you see, previously, we'll compare actually. Previously, we were applying standard convolution. Okay, I'll show you. So this was the standard convolution where we were going from 7 cross 7 cross 3 to 5 cross 5 cross 128 using a standard convolution. And what was that? A filter of 3 by 3 and 128 such filters. Now we are doing the same thing, but in 2 steps, right? We are going from 7 by 7 by 3 to again 5 cross 5 cross 128, but now there are 2 steps. The first step is a depth-wise separable convolution followed by a 1 by 1 convolution, right? So these are the 2 steps which you see on a single screen, that the input and the output are same, but now we have 2 steps. The first step is depth-wise separable, and then you have 1 by 1 convolution, which is called another name for 1 by 1 convolution is point-wise convolution. Now, why we are doing it? Of course, as I told you, lesser computation. Now, why they are lesser and how much they are lesser? Rather than just believing my word, let's compute it. Okay, let's see how many multiplications we are doing in each of the 2 different scenarios. Okay, so this was the standard convolution. Okay, let's see how many multiplications we are doing. So in order to compute one value here, what is your filter size? 3 cross 3 cross 3. So in order to compute one value, you are doing 27 multiplications, right? How many values you are computing total? 5 into 5 into 128, right? So it is 5 into 5 into 128. It's exactly the same thing which we did in the beginning of the lecture, that first whenever you have to find the number of multiplications, you see how many multiplications are involved in one convolution, which gives you one value, right? So the first part is how many multiplications you need for one value, and then you see how many values you need. You need as many values as the size of the output. So total values you need is 5 into 5 into 128, which is the second part. You multiply them together. So the total number of multiplications is, say, around 86,000. Okay. Now let's see how it will change if we split it into two steps, right? So maybe we can discuss from this, right? And I show you stepwise rather than we see in a single go. Okay, so you see here, in order to compute one value, the total number of multiplications is 3 into 3 into 1, okay, to compute this one value. And how many values we are computing? We are computing 5 into 5 into 3. Okay, so 5 into 5 into 3. Okay, this will be some number which you can see in the next slide. Okay, so this is basically the number of multiplications you have in the first step. Now, in the second step, in order to compute one value, what is your size of filter? 1 cross 1 cross 3. Okay, if you compute one value, and how many values you are computing? 5 cross 5 cross 128. Again, you can find it would be some number, and you just add them together, so you will get the total number of multiplications in this case. Okay, so these calculations are done here, right? So in this case, the first step is 675 multiplication. The second step is 9,600. If you add them, you get 10,000 something. Okay, so now you see, with standard convolution, the total number of multiplication was roughly 86,000. If you split it into two, your total number of multiplications is nearly 10,000. So from 86,000, we come down to around 10,000, which you can see is basically a very big gain, especially once you think that these numbers would be in millions. So actually, you are gaining a lot, right? So this was, you can say, our last model in the Inception family. Now, if you have some queries, we can discuss before we see something else. Okay, so maybe we can see just one last model for today, and then maybe we can conclude, right? So we have seen Inception family quite in detail, right? And as I told you that the key building block was Inception. The general idea of Inception was using multiple filters, right? But since it was increasing the computational complexity, so one by one convolution or bottleneck layer was introduced. And then certain improvements were made, like introduction of batch normalization in Inception V2, and then factorized convolutions in Inception V3. Right? And then we had seen exception, which is depth-wise separable convolution, where the idea is to reduce the number of computations. But as it was discussed and raised by your colleagues as well, that when we are trying to reduce the number of computations, then the feature extraction can be suboptimal, right? We may not necessarily, but we may have to compromise on feature extraction, right? So with that, now we move to our, you can say, the next very popular architecture, which I'm sure if you are doing some thesis, you are likely to use it, which is very, very famous, which is called ResNet, right? And Res is actually short for residual, right? When you see the name ResNet, so this res is actually short for residual. So basically, it is a residual network or residual learning, right? And again, it is considered a very major breakthrough because with the introduction of ResNet, we were able to train very, very deep models, right? And when we say very, very deep, it means we are not talking about tens of layers, rather we are talking about hundreds of layers, okay? And what actually led to this idea of ResNet, it was basically an observation that when people were making their networks deep by adding more layers, so there was a point that instead of getting better performance, the performance was actually decreasing, right? So the ResNets actually came to scene from the observation that why do deep networks perform worse when we add more layers? Ideally, what should happen that if we add more layers, the performance should improve. Theoretically, it should be like that. Okay, but practically what was happening was that, you see, this is the output from the, this is a screenshot from the paper of ResNet, that there are two models. One is 20 layer, the other is 56 layer. Okay, so it means the red one is actually deeper. And this is basically, you can say, some iteration of training. So on the training data, the error of 20 layer is less as compared to 56 layer. It means the 20 layer network is performing better. And similarly on unseen data, when you give the unseen data during training, so here we again have the same trend, that the 20 layer model has a low error rate as compared to the 56. So it is a deeper network which is actually giving you more error, right? So this basically this observation led researchers to dive into details that why this is happening, and eventually they came up with this solution which was called residual learning, right? Now, why deep networks are hard to train? Because there is something which we discussed informally earlier, which is called vanishing gradient problem. Now, what is that? Let's discuss it slightly in more detail as compared to what we have seen previously. Suppose there's a very, very deep network, okay, maybe 10 layers or 20 layers or 100 layers, right? So if you remember back propagation, okay, so if I have to update the weight of this first layer, my error is here at the last layer, okay? So we have to compute the derivative of error with respect to this weight, okay? But since this error is not directly dependent on this, what do we use? We use chain rule. Okay, if you remember chain rule, what will happen actually? You will have derivative of error with respect to some variable, say a, then you have derivative of a with respect to something else, which is b, and so on, b with respect to c, and eventually you will have, say, derivative of z with respect to w, which is actually this w. Okay, because you have so many layers in between. Okay, so you will have a chain rule which will have so many terms, maybe 100 terms or 150 terms or whatever the number is. Okay, of course, these will be different values, but just assume that all of these values are, say, 0.1. It means it is 0.1 into 0.1 into 0.1. So if these are 100 terms, so it would be 0.1 raised to power 100. Okay. Now, if you remember the weight update rule, how weights are updated? Weights are updated as weight plus learning rate into derivative of error with respect to weight. Okay, this can be minus or plus depending upon what convention you are using, right? Anyways, so you see now this term is actually very, very small, close to zero. So if your initial weight was, say, 2.0, right, you have 2.0 plus or minus, say, learning rate into something which is close to zero. So actually your new weight is like is the same, which was the previous weight, right? Because you are adding something which is close to zero. So your weight is actually not updating, right? It means that initial layers have weights which are not updated. Why they are not updated? Because the error term, because of this chain rule, it is so small that when you update the weight, it actually does not change. So your performance is actually saturated because now you are continuing training, but the weights are not updated, right? Because that term is very small. So this is actually what is called vanishing gradient problem, right? Okay, so there were many solutions suggested to this, right? But the most effective one was this, which is the residual learning. So in order to understand this, we see two layers of this network. This A is for activation, this superscript L is for layer number, right? So we have this layer L, L plus 1, L plus 2, okay? So how do we compute the output for, you can say, some layer? We have this activation AL, which is this. We multiply the weights WL plus 1, which are here. We add bias and we get ZL plus 1. Z is the notation we are using before activation function, okay? And then on this Z, we apply some activation function, which we are representing by G here. So we get this AL plus 1, which is actually this one, okay? Next, what we do, we multiply this AL plus 1 by the weights of this layer. We add bias, so we get ZL plus 2, and we apply activation on this Z to get AL plus 2. Right? So it is actually the same process which we have been doing previously. So this is actually, you can say, a visual illustration of what is happening. We have AL, We take a dot product activation function, we get AL plus 1. We take the dot product activation function, we get L plus 2. So this is your main path, okay, that how information is flowing. And this is actually the representation of this, that you apply activation function on Z L plus 2, so you get AL plus 2. Okay. Now, in case of a residual network, what we do is we add a shortcut connection in addition to this main path. Okay, and what we do, we have this AL here, we copy it and we add this path. So we add this information somewhere in the future. It means we skip this part, okay, and we add this information at this point in time. So now information is flowing on the main path, just like it was flowing previously. And we also have this shortcut path, which is picking the information which was here, which was AL, and it is adding this information somewhere in the future. By future, I means ahead in the time or ahead in the layers. Now, what actually will change? Now, instead of this expression, now our expression would be activation function applied to this. This is coming from the main path. And you also have this, which is coming from the shortcut part or the skip connection, or the, you can say identity connection. There are many names for this. So now your expression for A of L plus 2 has changed. This is a new term which you have added. And the second term you see in this expression is coming from that shortcut path, right? So this is a very famous, you can say, illustration that you will see whenever you see a tutorial on ResNet, right? That you have information which is flowing in this normal direction. You just copy this information and you add it by skipping 2 or 3 blocks. In this example, we are skipping 2 blocks. And this connection is called a shortcut connection, a skip connection, or an identity connection, right? So what we do that in ResNet, just like in Inception, we had Inception block. In ResNet, we have a residual block, right? So this is one residual block where we have some layers, which can be 2 or 3. And to these, we are adding this shortcut connection. And now this is one block, you can repeat it k times or n times, you can stack them together and you will end up with a residual network. Now by adding these skip connections, what was observed? That you see, previously we were saying that theoretically adding more layers, the error should go down. But practically after certain number of layers, the error was going up, right? This is what is happening before ResNet. But after ResNet, what was happening? That as we were adding layers, the performance was actually, or the error was going down and the performance was actually improving. So why is it happening? I tell you in a while, right? But before that, as I told you, that in the original ResNet versions, there are 2 different propositions. One proposition is that you skip 2 blocks, okay? So the small networks like ResNet 18 and 34, the skip connection is skipping 2 blocks, right? This is block 1, block 2. So the skip connection is like this. And there are further deeper version like ResNet 50, 101, and 152, in which they are skipping 3 blocks, right? So if you come up with your own architecture, you may choose to skip maybe 4 block or 5 block. It actually depends what you are trying to achieve, okay? Now, the last thing for today, that why this is happening, okay? You can say, okay, adding the skip connection, why the performance is not degrading, right? Because previously performance was degrading. So what magic actually is being done by this skip connection, right? So we'll just quickly see the intuitive reasoning of why is it happening. So you see, suppose this is some big neural network with say 10 layers or 15 layers, which is having this input X and it is giving this activation as an output, right? Now to this network, we add 2 more layers, right? Layer L plus 1 and L plus 2. And we also add this skip connection, okay? And all of these layers are using ReLU activation function. So after application of ReLU, there are no negative values. So just keep in mind that all the activations are either 0 or positive, right? We don't have any negative values in activation because we are applying ReLU activation function. Okay, now let's see what is actually happening. Now AL plus 2, which is this, is actually activation function applied to ZL plus 2, which is coming from the main path like this. And then this A of L, which is coming from this shortcut path, right? Just like we said previously. Now this ZL plus 2, it is actually weights multiplied by activation plus bias, right? So we have just expanded this term just like we did previously. Now this is actually the important discussion. you see, we have seen regularization, right? And we know that we have mechanisms where we can force the weights to shrink or to go close to zero. Now, if somehow we make these weights close to zero and this bias also close to zero, so what will happen? This term is gone, this term is gone, and we are left with this one, A of L, right? So we are left with A of L plus 2 is activation function applied to A of L. And why? Because somehow we force the weights to go close to zero. So eventually, if the first two terms are gone and we are only left with this one term. Now, this A of L is actually activation of a layer on which ReLU is applied. So when you apply ReLU, it means all the values in this A are actually positive. Okay. So if you again apply a ReLU activation function, you get the same thing, right? So you see, if I have a number -5, I apply ReLU, I get 0. Now, if I again apply ReLU, it will stay 0. Similarly, if I have a number which was +2, if you apply ReLU, you get 2. If you again apply ReLU, you get the same number. It will not change, right? Because first time once you apply ReLU, you got what you wanted. So applying again activation function on this will actually give you this thing. So now you see what is this? A of L plus 2 is same as A of L. Now what does it mean? That this is actually same as what you are getting here if your weights of these layers somehow you can make them go to 0. Now, in other words, we can say that the new layers which you have added with a shortcut connection, which we call residual block, it is very easy for residual block to learn identity function. Now, what is identity function? This is identity function that you get back the same thing. How it will learn identity function? It can simply shift the weights towards 0. Okay. And once the weight becomes 0, actually you are getting the same output, right? So that's why we say for a residual block, it's very easy to learn the identity function. Now, what will actually happen? When we are adding these two layers, if the network thinks that these layers are not required, what it will do? It will easily shift its weight towards 0, right? And whatever you were getting performance with these network, after adding these two layers, you will be getting the same performance, right? It means adding these two layers will not hurt the performance of the system, because if these two layers are not required, your network will shift the weights towards 0 and your performance will stay where it was, right? But you see, our goal is not to keep the performance same. Our goal is actually to improve the performance, right? So if you see it from that perspective, now by adding the identity function, you have a baseline that you have a guarantee that performance will not degrade. Okay, that performance will not degrade. Now you have ensured that adding layers will not degrade the performance. And if these two additional layers learn anything useful, then there is only one possibility, and that possibility is that you will improve things. Okay, so you see how we smartly did it, that first we guaranteed that performance will not go down because we made it very easy for the network to learn the identity function, which will ensure that the performance does not go down. So this identity function is like your baseline. Okay, that minimum you will get what you were getting previously. And if this is your baseline, either you will stay where you were or you can only improve, right? You will not go down. So this is basically the key reason that when you add a residual connection, your performance does not degrade as it was happening in case of you can say previous networks, right? So quickly, how can you convert a simple network into a residual network? Say this is your conventional network with pooling and convolution and all that, right? So you see, you just add these residual connection or skip connection, so you can convert any regular network into a residual network, right? And just one last word on this, that it was so, you can say, such a breakthrough idea that in 2015, in 5 different tracks, the same, you can say, residual network, which was 152 layers, it got the first rank in, you can say, all of these 5 different tracks, right? Not only just image classification, but detection, localization, and this COCO is a different data set, right? And the performance of this model in image classification was better than human, right? When the same task was performed by human, the error was more than what this model reported. And to be precise, this number was 3.6%, right? So that's why this is a very, very, you can say, effective model. And if you are solving a complex problem, then of course, this is the model you should try for, right? So with that, maybe I'll stop here for today. If you have any comments or points, please let me know.